Hello, this video is on how to read an NMR in organic chemistry. NMR is a tool used in organic chemistry to determine the structure of organic molecules, and it works by identifying some characteristics of hydrogens on those molecules. NMRs look something like this, with a section upfield closer to 0, a section downfield with larger numbers, and multiple peaks, which have certain integrations or areas under the curve. The location where they're placed, along with how large the peak is, tells you information about what hydrogen that peak corresponds to. So the first thing you should do when reading an NMR is to identify the index of hydrogen deficiency, which basically tells you how many double bonds or rings there are in the structure. And you calculate that by using the molecular formula for the molecule. So the formula is the index of hydrogen deficiency is 2 times the number of carbons plus 2 minus the number of hydrogens plus the number of nitrogens minus the number of any halides there might be, and all that divided by 2. So, for example, if you take this C9H10O2, the IHD of this molecule would be 2 times 9 plus 2 minus 10 plus 0 because there's no hydrogens, and minus 0 because there's no halides. All of that divided by 2. And that equals to 18 plus 2, so 20 minus 10, which is 10 over 2 equals 5. So basically that is how many double bonds there are, or how many rings there are. So a double bond uses up 1 of this in hydrogen deficiency. A triple bond takes up 2, and a ring takes up minus 1. Well, it takes up 1. So if there was a ring, that would be 1. This will come in handy a lot when you're putting things together. One thing to note is that that is for each, that number, that cost of 1 is for each double bond. So something like benzene, which has, if you draw it like this, 3 double bonds and a ring, that is an IHD of 4. And a lot of the times, if there's an IHD of greater than 4, a lot of the times it's going to be a aromatic ring. Another thing to keep in mind is solvent peaks. So within the solvent, there are peaks used to coordinate. The most notable one is the singlet peak at 0, which you can see on this diagram right here. You can just ignore that, because that is based on the solvent, and it is not based on the molecule. Some other peaks you might see are a singlet peak at 7.26, which you can see in this one right here, and which is because of chloroform impurities in deuterated chloroform, which is used as the solvent, and a peak at 1.56, so right around here in this one. This one also has the chloroform peak. The peak at 1.56 corresponds to water in deuterated chloroform. So one of the main important parts of the NMR diagram is the shift. Rightmost is upfield, closer to 0. Left is downfield, higher numbers. This depends on the electron density of the specific hydrogen. If there's more electrons near it, it shields more from the magnet, the strong magnetic field, so shows up farther right. If there's less electrons near it, it's not shielded as much, so it appears farther left. Ways this electron density is modified. So such things are double bond character. So if it's near any double bonds, say like a aldehyde, that hydrogen is, a lot of the electron density is going towards the double bond, so it would be a lot less shield farther downfield. And electronegative atoms nearby. So say if there was an alcohol, this would also push it left. So some common shift ranges. Sometimes your professor will give you a cheat sheet that looks kind of like this, with all these numbers, or something like this. But it is good to remember a few of them, because it's just a little faster that way. But if you do have one of these, it's very useful to reference. So some common shift ranges are some messy peaks. By messy, I mean there's quite a few of them, and it's not exactly singlet or doublet or anything like that. I'll get to that later on. But it looks... let me see if I can find one. It looks something like this, where it's not quite a distinct single peak, but it's a little broken up. And if it's right around somewhere between 6.5 and 8, that typically means an aromatic ring, so like benzene or substituted benzene. If there are peaks close to 1, say like this one right here, typically that means it is a sp3 carbon with hydrogens on it. 2 to 2.5 is carbonyl, so the alpha carbon of the carbonyl, so like right there. Also in that range are carbons adjacent to aromatics, so say toluene would have a peak right around 2 to 2.5, as well as the aromatic hydrogen peaks. 4.5 to 7 is the sp2 carbons. That's the ones you'd find on alkenes. 9 to 10 is where you'd find the hydrogen of an aldehyde. The double bond character and the oxygen there really take away the electron density, pushing it quite far, shifting it quite far left, deshielding. And all the way at 10 to 13 is carboxylic acids, which is basically even further taking away that electron density. So splitting is another feature of NMR graphs. I wouldn't rely on it that much, because if you get diagrams something like this, the detail is a little fuzzy, so you can't really tell. But if you do have it, it is useful for determining the number of neighbors. By neighbors, I mean, so there's the hydrogen there, carbon, whatever it is there, and say whatever it has there. So if we're talking about the peak for this hydrogen, these would be its neighbors. So 1 carbon away, and any hydrogens attached. One, not necessarily carbon, but any non-hydrogen atom there, attached to whatever it was attached to, those are the neighbors. So if you see in this one, we have labeled A, B, and C. So A, since there's no, their hydrogens are sticking off here, and this is the only neighboring atom, like that one. Since there are no hydrogens there, it has no neighbors, so it would show up as a singlet. So the way the number of peaks, the splitting, looks something like that. How that's calculated is it's just the number of neighbors minus 1. So, no, plus 1. So no neighbors would be a splitting of 1, so a singlet. If we look at B, it has 3 neighbors here, all on this one. So it have a splitting of 4, a quartet, and this one here has 2 neighbors both here, and have splitting of 3, so a triplet. Again, don't rely on this too much, because a lot of the times your diagrams will be really fuzzy and you can't tell how many neighbors, what the splitting of it is. So it's advantageous to just go off of, rely mostly on integration when you can. And integration, I don't know if I mentioned this earlier, is the height of the peaks. Well, not necessarily the height, but the area under the curve of the peak. This will typically be given to you, so say here it's labeled as like 6H, 1H, 2H, 1H, 2H, or like on this one it's drawn underneath there, as in like 3, 2, 2, 1, and then 1.9. You can kind of just round to the closest whole number. So here it's like 5 and 2.1, just round that one to 2, and that's basically the integration. That is the number of hydrogens at that peak. So say here, since there's 3 hydrogens, this one would have a signal with a peak integration, a peak with an integration of 3. This one would have an integration of 2, this one would have an integration of 3. This is not just from one, not necessarily just from one carbon, it's all of them that have the same exact environment. So say on a tert-butyl group, all the hydrogens on each of these methyls would have the same exact environment, so would share the same exact peak, and boost the same integration. So some common structures, the integration of these, as I just said, tert-butyl groups, like this one, would have a peak of 9, integration of 9, which is usually the highest you'd see. If there's an integration of 6 and an integration of 1 in 2 separate peaks, that is most likely an isopropyl group, because you got the 3 ones on there, 3 ones on there, those go to the 6, and the 1 hydrogen on this carbon, which would go to the 1. If you see 3 hydrogens and a bunch of 2s, it is most likely, it is very frequently a chain like this, where the terminal one has that 3 hydrogen and these ones here have the 2s. Again, no, not again. If you have something that's like the messy 5, like this one, the integration of 5, that is usually a substituted benzene looking something like this. That R is going to be maybe like a carbon or something. If it's 1, 2, and 2, all also around that 7 range, so like up here, odds are that is going to be also a substituted benzene, but with like a strong unshielding substitution there. So like a carbonyl or an oxygen could cause that effect. Some final information about this. Splitting, as I said before, not always available due to blurry imaging. And some additional information you might find in questions. So decolorizes bromine or reacts with hydrogen gas and a metal catalyst like palladium, platinum, nickel. That indicates an unsaturated molecule, say like an alkene. which the bromine would attack, or same thing with the hydrogen and the metal catalyst, that would also stick hydrogens on that to saturate it. That also is carbonyls, so ketones kind of thing, which would, in the case of hydrogen and metal catalyst, convert to an alcohol, and in bromine, that would cause an addition, I believe. Maybe. Also, reacts with sodium to form gas, or hydrogen gas. That means it's something that can be deprotonated. So say a carboxylic acid, the sodium would attack this, steal that, to become a, it would steal this hydrogen, that would go to hydrogen gas, alcohol, that would replace the hydrogen, basically. So, on to some practice questions you might be seeing. What is this? So this one, we've got 3 separate spectra, each have the same C4H8O2. So if you do an IHD of that, you get 8 from the carbons plus 2 minus 8 all over 2. Oxygen has no effect on the IHD. Those cancel, so we just get an IHD of 1, which means that there is either there's a double bond somewhere. So either in it's either in a alkene or a carbonyl. Since there's oxygen, it's usually a carbonyl. So this is what I meant about the splitting being indistinct. It's kind of hard to see, but we do have the integration, so we can figure it out from there. Since we have a 3, we know that there's a terminal end of the chain somewhere with 3 hydrogens. And these 2's, since this one's all the way down here, it is... Oh, let's start with this one. We have a single integration at 8, which corresponds to right around here. Sometimes it's a little out of range than what you'd expect. So right around 8. It's a little hard, but this might be a aldehyde. So if we look at this, it might be something like this. If it's not correct, you can just keep trying and retrying. It's a lot of trial and error with this, of trying to figure out what works and what doesn't. So when you have something that you think might be it, it'd be beneficial to check the structure to see if it makes sense. So we have a 1 all the way over here, far shifted downfield. A 2 that is not as shifted downfield, but close to a oxygen. So over here, we can see those are usually around 3.6 to 4. This is right around 4, so that would make sense. Here we got maybe like 1.6, 1.7, which is reasonable for something right around here. It's not a specific number anywhere on this sheet, I don't no, there is. It's 1.4 here of 1 away from an oxygen. So that makes sense right around there. And we got a 3 here corresponding to that one. So this one seems to be the correct answer. We got the same, for compound B, we got the same exact formula. So it's 1 IHD. Got a 3, a 2, and a 3. The 3 is at 4 close to 4, so we know that from here it's most likely the oxygen side of an ester. Then we got a 2 and a 3. Between 2 and 3, we got the alpha carbon and the carbonyl right there. So that makes sense. And once again, close to 1, we have just a 3. So this seems to be the correct answer for this one. Compound C, same thing. Same IHD, same molecular formula. We got a 3, a 2, and a 3 again, but they're in different places. Since this one's 2, and it's closer to like 4-ish, we know that it's the oxygen side of the ester. So it's going to look something like this. The one right around 2 is the peak of 3, and you can actually kind of see that it's a singlet. So if you did have information like that, it would be useful. So that makes sense. This one makes sense. Once again, right around 1 point something. We got a 3, so this one also seems to make sense. Next question. Oh, the previous one was, I don't know what that was in the textbook. This question's 13.16, so the previous one was probably 13.15. Following H NMR spectrum for compounds D, E, and F with formulas C6H12. So IHD, calculate that one right away. So that's 12 minus 12 plus 2, so an IHD of 1. Since there's no oxygen in here, that means there's one double carbon-carbon double bond somewhere. That each readily decolorizes a solution of bromine. As I said before, that also suggests that there's a alkene double bond in there. Propose structural formulas and account for observed patterns in signal splitting. So it's a bit hard to see, but we can figure it out anyway. So we got a 6, 1, 2, 2, and 1. As I said, 6 and 1 is typically isopropyl group. So we expect that it looks something like that. 2, 2, and 1. Here's where it gets a little more difficult. We know the range of this, of around 4 to 7-ish for alkenes. Since there are 2 of those in range, those 2 peaks, 2H and 1H, we can guess that the alkene is all the way at the end of the molecule, rather than somewhere in the middle. So it might look something like this. So these 2 would go here, and that 1H would go here. 2, 1, 6. So 2 would be the spend here. There's the isopropyl, so that's what I guess would look like this. If we try to do the splitting, I don't know if you can see it. This 2 seems to look like it has a splitting of a triplet. So there's one neighbor there, so that makes sense. This one has a multiplet splitting, so it can't really tell, but there's a lot of them, so that would make sense since there's 3 here and 3 there. The 6H looks like a doublet, so one neighbor there. This one here, it's fuzzy, but there's a lot of them. There's one neighbor there, and 2 neighbors there, so a quintet maybe. So this seems to make sense. Compound E, same molecule structure, same 1, but this time we got 3, 3, 3, 2, and 1. Let's see. So we know there's a double bond somewhere, so we can just draw that right away. Since there's no 2 in that range, we can guess, since it's actually only just 1 in that range, we can guess that this is 3 of the 4 places on that double bond are going to have something substituted. C6, 1, 2, 3, 4, 5. Somewhere else there's a carbon somewhere else. So we got 2, 3, 3, and 3. Okay, so we can guess that one of these carbons here has the... No, we can't guess that. Since we see that there are some splitting on this 2 and this 3, we can guess those are together. So let's see. Just remember, you can try something. If it doesn't work, try something else. These 3 are very similar, so that might suggest that they are very similar environments like that. This one here, this 2 would be this one. These 2 3s would be here. This 3 would be over here. That seems like it could be plausible. It's a little hard to tell, though. Compound F. We got a 1, same molecule formula, same IHD of 1. Got 1, 2, 1, 2, 3, 3. So let's see. This 1, 3, 3, 2, 1, 2, 3, 3 makes me think that it might be something like this with something here. We see the same 1 and 2 on the right there, so I think it might be something like that. See the 1 with a lot of things nearby, and it's farther shifted, so it seems to be that it would be closer to this. We got a 2 here, and 2 3s. So this seems plausible, as this could be what the structure is. We know it's not the same. We know it's not this, because this is this, and it would look different with these being the exact same, but since they're different, it might be something like this. I would recommend checking the answers in the textbook. These are just my guesses. We got question 13.17. Some more of this. NMR spectra with compounds G, H, and I. C5H12O. So calculate IHD again. So we got 10 plus 2 minus 12. So that's an IHD of 0. So it's completely saturated. Each is liquid at room temperature, slightly soluble in water, and reacts with sodium metal with the evolution of a gas. So that's what I said before. Since there's no IHD, it can't be a carboxylic, and there's only one O, it can't be a carboxylic acid, so it's definitely an alcohol of some sort. All three of these. So let's just see what we can do. Got a 6H, a 3H, 1, 1, and 3. Oh, 1, 1, and 1. So we can guess that this one all the way farthest left is the OH of the alcohol. That just leaves the rest of these. This 1 and this 6 seems like it could be an isopropyl. And this 3 and this 1 seems like could be something like this. So we got the 3 here of this one, the 1 of here, the 1 here, the 1 here, and the 6 that are these combined. This seems to make sense. Okay, compound H, same formula, same IHD of 0. Once again, we got a 6, 1, and 2, a 1, and a 2. This is more difficult. Maybe it's an ether. No, can't be an ether because we know that it reacts with sodium metal. Just draw that in for now. 2, a 1, and a 2. No. Oh, no, that's what it is. This peak right around a bit less than 2 is the singlet peak, it appears, so that's probably this one, not this one. And this one all the way out here is probably this one. So if we look at it that way, it might look something like this. So we got hydrogen there and there. Those are those. This one is this. Got a 2 being those ones. A hydrogen here. And the 6 from those. So this one seems to be what this one is. Finally, compound I. Same exact formula. Same exact IHD. Got a 3, 2, 1, 2. And this signal is an overlapping pair of 2H multiplets, which suggests something kind of weird going on. But keep going, carrying on. It's got this 2 and the 1, so that's probably the OH at an end somewhere. this overlapping 2H multiplets seems like it would be something very, two very similar groups like that. And we got a 3 at the end. 2, 2, 2. No, we're missing 1. 2, 3, 4, 5. There we go. So we got 3, 2, 2, 2, 2, and 1. So this seems like it would be the structure of this. I think that's all the time I have for this, so good luck.